So we had a look at what is multicollinearity, and we also had a look at what could be the possible sources that cause multicollinearity in the sample that we have with us. Now, the important question is, what happens, what if there is multicollinearity? What goes wrong? What happens? What is the problem with multicollinearity? The first and foremost problem that we have is that it becomes very difficult to estimate the true population parameter with great precision. Now, the reason is, if you have highly correlated X variables, the standard errors of your sample estimate, that is your sample beta 2 hat, beta 3 hat and so on, their standard errors become very large. Okay. If your multicollinearity is perfect, that is perfectly linearly related X variables if you have, the regression coefficients are indeterminate. That is, they cannot be estimated at all, and their standard errors will reach infinity. Okay. If it's the case that you have less than perfect collinearity, you can determine and calculate your regression coefficient, but they will still have the problem. They will still have the problem of very large standard errors. That is, we are talking about large standard errors in relation to the coefficients that have been calculated. If you have large standard errors, it affects the precision with which, or the accuracy with which, the true parameters can be estimated. To understand this better, I have just copied our 3 variable model, if you remember, where you have yi, x2 and x3 are the 3 variables, and I have written it in the deviation form over here. Right, so this is in the deviation form. Small yi means observation capital Yi minus y bar. Similarly, x2i is also in its deviation form, that is capital X2i minus x2 bar. Similarly, capital X3i minus x3 bar, right? So this is the model, the 3 variable regression model in the deviation form. So based on this, these are the 2 formulas for the 2 coefficients beta 2 hat and beta 3 hat, right? Now, if you assume that you have perfectly multicollinear x2 and x3, so that can be specified like this. x3i is lambda times x2i. So that's a perfect linear relationship because there is no error term on the right hand side. Okay, and lambda is something different from 0. It is not equal to 0. So if you have a perfectly linear relationship between x2 and x3 of this sort, if you try and substitute this relationship over here. So instead of x3i over here, I am using lambda times x2i. So, and over here also, instead of x3i, I have substituted lambda x2i. If you put it in, you can see that you have a 0 by 0 form. I hope you remember that 0 by 0 form means it is an indeterminate value. So if you have perfectly multicollinear relation or perfect linear relationship between your x variables, your coefficient beta 2 hat cannot be determined. It is indeterminate. Now another way of looking at it is, like I said, your x3i is lambda times x2i. So instead of x3i, this is my original, if you remember, my original deviation form equation was yi is equal to beta 2 times x2i, small x2i, plus beta 3 times, I am writing the sample regression function, okay, beta 3 times small x3i plus ui hat. Now I know that assuming x3i is lambda times x2i, if I substitute it into this model, I'll get it in this form. As you can see, beta 2, sorry, one second. As you can see, you can beta 3 times lambda x2I has been substituted. So you can write this as beta 2 hat plus lambda times beta 3 hat times x2I plus ui hat. So if I run this model, I will only get the value of one coefficient, which is alpha hat, where alpha hat is actually a linear combination of beta 2 hat and beta 3 hat, right? So if there is multicollinearity, and I am saying exact multicollinear relationship between the two x variables, I can only manage to estimate alpha hat accurately. It will be impossible for me to estimate beta 2 and beta 3 hat independently or uniquely. For every value of alpha hat, if I assume any value of beta 2 hat, I can get a corresponding beta 3 hat value can be calculated, right? So there are infinite number of possible solutions, possible values that beta 2 hat and beta 3 hat can take given an estimated value of alpha hat. Okay, just one small correction here. It should be beta 2 hat and beta 3 hat uniquely. For example, if I calculated and found that alpha hat is 0.8, right? If I say that beta 2 hat is 0.5, then I can find out beta 3 hat as alpha hat minus beta 2 hat divided by lambda. So for given value of lambda and alpha hat, any value that I assume for beta 2 hat, I can find a corresponding value for beta 3 hat. There are infinite possible combinations for given alpha hat and lambda. So it is impossible to determine or estimate beta 2 hat and beta 3 hat uniquely. Okay. Now if you have less than perfect multicollinearity, then you can estimate beta 2 hat and beta 3 hat. It is not impossible. But the problem remains that these coefficients that have been estimated will have very large variance and covariances. Large variances and covariances will affect the precision or the accuracy with which we can estimate our true population parameters. So what are the theoretical consequences of multicollinearity? First thing to be noted here is that even if you have near or high multicollinearity among the x variables of the regression model, the OLS estimators will continue to be blue. That is, they will be best linear unbiased estimator. Our Gauss-Markov theorem is still holding that in the entire class of linear unbiased estimators, it is the OLS estimator which will have the least variance. That being said, even though they have the least variance, they will not have the variance value itself will not be small. The standard error therefore will not be small, they will be quite large. Every time we say small or large variance or small or large standard error, we are saying relative to the value of the coefficient, the values of the standard errors will be quite large. Okay. Another point to be noted is that having too small a sample, that is, you have a sample which is not large enough, that too can have the same effect of blue estimators where the standard errors are too large. So the effect of that will be the same as the presence of multicollinearity. Not having a large enough sample size, the problem is called micronumerosity. Okay, this is the case when the sample observations, the total number of observations in the sample barely exceeds the total number of parameters that have to be estimated. Remember, I told you the example of how in the case of research in medical practice, medical field, where you have a few number of patients but you have data and regarding several explanatory variables, often the problem of micronumerosity arises. That is, your sample is not large enough. The problem of micronumerosity, or the consequence of this micronumerosity, is the same as the consequence of multicollinearity, which is our OLS estimators are still blue, that is, they still have the minimum variance in the entire class of linear unbiased estimators, but the variance and covariances and standard errors are very large in relation to the coefficient that has been estimated. So, if there is multicollinearity, is the OLS estimator unbiased? Yes, it is. Okay. What does unbiased mean? That if you take repeated from the same population, keeping your x variables fixed, if you take more and more samples, different samples, and calculate the OLS estimators for each sample, the average of these estimators will be equal to the true population parameter as the number of samples increase, right? As you take more and more samples and calculate the OLS estimators, the value or the mean value of the estimator will converge to the true population parameter. So, even if there is multicollinearity, our estimators, OLS estimators, are unbiased. And like I said, even in the presence of collinearity, in the class of all linear unbiased estimators, our OLS estimator still has the least variance. This is also known as efficiency of the estimator. So it is still the most efficient estimator. But it does not mean that the variance will be small in relation to the value of the estimator. Another point to be noted is that often multicollinearity is a sample phenomenon. What that means is, maybe in the population as a whole, the x variables that have been chosen are not linearly correlated. However, we assume that the x variables are fixed. So, in the sample that we have at hand for our calculation and estimation purposes, it is possible that our x variables are highly correlated. Okay. If you have a look at the Gujarati book, it mentions an example of the consumption expenditure model, where the consumption expenditure is your y variable and it is being determined by income and wealth as the x variables. Now you know that both income as well as wealth of the are variables that will tend to be highly correlated. Mostly or most often we'll find that wealthy individuals also have high income, and people with low or less wealth will tend to have lower incomes. So the sample that we have at hand might be such that these x variables are highly correlated. If our sample is wide enough and rich enough to include all combinations of people, that is, people with high income but low wealth, as well as people with low income but highly wealthy, if we have such a rich sample, then it is possible that we can get rid of, or we can avoid the problem of multicollinearity. So even if in the total population, income and wealth are not as correlated as we see, maybe the sample that we have at hand, the correlation is high.